Hello, in this video we're going to go over the final exam from spring of 2024 for multivariable calculus. So here is the first problem. Find an equation of the plane that contains these 3 points. So the first thing we need to do in order to find an equation of a plane, we need to find one point and a normal vector. We are given 3 points, so we'll find 2 vectors on the plane. One of them is the difference of the first one and the second one, so 1 0 -1 and -5 3 2. So that would be a vector on the plane, so this would give us 6 -3 -3, and then the second vector would be difference of two others, so 0 1 1 0 -1 minus 2 -1 4. So when we take the difference of these two, we get -1 1 and -5. Next we'll have to find the cross product of these two. So the normal vector would be I j k 6 -3 -3 -1 1 5 -5, which will give us, so eliminating the first column we get 15 plus 3i. Eliminating the second column we get minus 30 minus 3j, and eliminating the last column we get 6 minus 3k. So this is going to be 18i plus 33j plus 3k. So that is a normal vector. So the plane is going to be 18 times x minus, so we can take one of the points, we can take 1 0 -1 plus 33 times y minus 0 plus 3 times z plus 1 equals 0. So that would be our answer. Do the planes this and that intersect? If so, find a parametric equation of the line of intersection. So if we have two planes, when do they intersect and when are they parallel? They are parallel if the normal vectors are parallel to each other. They intersect if the normal vectors are not parallel to each other. So we're going to find the normal vector. So normal vector to the first one is 1 3 -1, and normal vector to the second one is 0 1 1. So these are not scalar multiples. So that means the two planes do intersect. So that's the planes intersect. Okay, so now we want to find the equation of the line of intersection. So in order to find the equation of a line, we need to find one point and we need to find a direction vector. So one point on both planes, clearly the origin is on both planes. So 0 0 0 lies on the line of intersection. Now we'll take the direction vector as cross product of the two normal vectors. So the direction vector is going to be the cross product of the two vectors, 1 3 -1 that we found, and 0 1 1. So this would be the a direction vector to the line that they gave us. So 1 3 -1 0 1 1. So eliminating the first column, we get 3 plus 1i minus 1 minus 0j plus 1 minus 0k. So this would be 4i minus j plus k. And they asked us to find a parametric equation. So the line would be x equals, so the origin is at the point on the plane, on the line, so we get 4t, y equals -t, and z equals t. So this is the line of intersection. Let's move on to the next problem. Find the distance from this point to the line described by that. So okay, so we need to find a point on the plane, on the line, so that is 1 1 0, and the point that we are given is 1 2 -1. Then we also need to find the vector in the direction of the line, which is 2 2 1. Now we find pp0 That is, so we'll have to subtract p from p0. So terminal minus initial, so that would be 0, negative 1, 1. And then we'll have to find the cross product of these two, because the distance, the formula for the distance is for the distance from a point to a line is the cross product of p0 and a direction vector divided by magnitude of v. So let's find the cross product of these two. pp0 cross v is going to be I, j, k, 0, negative 1, 1, 2, 2, 1. Okay, so eliminating the first column, we get negative 1 minus 2i minus 0 minus 2j, and then plus 0 plus 2k. So that would be square root of 9 plus 4 plus 4 divided by square root of 4 plus 4 plus 1. And this would be our answer. So we're going to simplify, although they didn't really ask us to simplify. So this would be, so this is 8 plus 9, that's 17, divided by 3. That's root 9, which is 3. So that's the distance. Next part of the problem is asking us to find the cosine of the angle between these two. So cosine of the angle would be 2i plus 3j minus 6k dotted with 2i minus 2j minus k divided by the product of the magnitudes. And they did ask us to simplify, so we will do so. 4 plus 9 plus 36, 4 plus 4 plus 1. Okay, so the denominator would be 4 plus 9, that's 13, that is 49, and that is root 9. Numerator would be 4 minus 6 plus 6. So this would be 4 over, so we get 49, which is 4, which is 7, root 49, which is 7 times 3, that is 21. And they didn't ask us to find the angle, they asked us to find the cosine of the angle. So that is our answer. Consider the parametric curve this, find the unit tangent vector and the tangential component of acceleration. Okay, so let's first find the derivative, and then we'll divide by its magnitude to get the unit tangent. So derivative of that would be 2t squared I plus 2t cubed j plus t to the fourth k. So this is the derivative of that. Let's take the magnitude and let's then divide. So magnitude of that is 4t to the fourth plus 4t to the sixth plus t to the 8th, and then square root of that. Now this can be simplified. This is 2t squared plus t to the fourth squared. This is the perfect square. They did ask us to simplify, so we will have to simplify this. So this would be 2t squared plus t to the fourth. So that is the magnitude of that. Next, we'll have to find the unit tangent, which would mean just dividing these two. So we get 2t squared I plus 2t cubed j plus t to the fourth k divided by 2t squared plus t to the fourth. Now we can cancel t squared. The numerator factors a t squared. We get 2i plus 2tj plus t squared k. And we get 2 plus t squared at the bottom. So this is the unit tangent. Tangential component of acceleration. There are two ways of evaluating the tangential component of acceleration. The way that I usually do that is by doing the dot product of acceleration and velocity and dividing that by the magnitude of velocity. There are a couple other ways of doing that as well. Sometimes this method is easier, sometimes the other methods are easier. So in order to evaluate that, we'll find the acceleration. So acceleration is just the derivative of velocity. We already found velocity, so we'll differentiate that. We get 4 ti plus 6t squared j plus 4t cubed k. Next, we'll find the dot product of acceleration and velocity. That would be the numerator. So this gives us 4t times acceleration was 2t squared, so I'll put it here, 2t squared plus 6t squared times the second component of velocity was 2t cubed plus 4t cubed times t to the fourth. All of that divided by magnitude of velocity, which is 2t squared plus t to the fourth. This is something we did earlier. Okay, so now we'll simplify this because they did ask us to simplify. So at the bottom, we can factor t squared. We get 2 plus t squared. On top, we can factor t cubed. We can also factor a 4. So we will get 2 plus 3t squared and then plus t to the fourth. Okay, so we can simplify t squared. So we get 4t times. And then this one also factors as t squared plus 1 times t squared plus 2 divided by 2 plus t squared. And this actually does simplify a bit further. So we can simplify this to get rid of this one. We get 4t times t squared plus 1. So this is the tangential component of acceleration. There is also another way of doing this one, which is taking the derivative of speed. And that would be a bit faster than this one. It has less computation. But depends on which formula you remember. I usually only remember this formula. Write down an integral that gives the length of the curve from 0 to 1. So what is the length of the curve? It is the integral from 0 to 1 of velocity, which we already evaluated. So it is 2t squared plus t to the fourth dt. And they specifically ask us to not evaluate. So we'll just leave it at that. Okay, so next problem. Write down a smooth parametrization of the intersection of the cylinder with plane y equals 5. So what is a parametrization? So let's draw a diagram here. So we have a cylinder based on the xz plane. So we have this cylinder and we are intersecting that with y equals 5. So we get a circle like this, y equals 5. And the radius is 2. So this would be 2 cosine of theta. Y coordinate is 5 and then 2 sine of theta. And what are the ranges for theta? They are from 0 to 2 pi. So that is all we need to do. They did specifically ask us to not show that it is smooth. So we don't have to take the derivative and show that the derivative is non-zero. Suppose that a particle moves with velocity that the particle passes through z equals 2. Okay, so if it passes through z equals 2, it means at time t equals 2, it means the third component is going to be 2 when t equals 2. So let's look at the third component of the position. So the z component of r of t is integral of t plus 1, which is t squared plus 2 plus t plus c. Now, at t equals 2, we get 4 over 2 plus 2 plus c. That would have to be 2 because that's what they told us. So that means if you simplify this, c becomes negative 2. So this means the z component of r of t is going to be t squared over 2 plus t minus 2. Now they said at what point does it cross z equals 4? At what later time? So we need this. We need t squared over 2 plus t minus 2 to be 4. So we'll clear the denominator. We get t squared plus 2t minus 4 equals 16 equals 8. So that gives us t squared plus 2t minus 12 equals 0. And then we can solve this for t by completing the square or by using the quadratic formula. So minus b plus minus root b squared minus 4ac all over 2a. So minus 1 plus or minus root, this would be 1 plus 12 if we factor 4. So this is minus 1 plus minus root 13. So they said at what later time? So the answer is root 13 minus 1, because it is a later time, not in the past. Consider the function, this calculate the gradient. So gradient, we just take the derivative, we get 2 cosine of x minus 3 sine of y and minus 2. So that's the gradient. Next part is asking us to find an equation of the tangent plane to the level surface at this point. So the normal vector would be gradient at pi over 2, pi over 2, 1. So all we gotta do is to plug in pi over 2. We get 0, negative 3, negative 2. So that's a normal vector. So the tangent plane would be using the point and a normal vector. So it is 0 times x minus pi over 2 minus 3 times y minus pi over 2 minus 2 times z minus 1 equals 0. So this is the tangent plane. Find the directional derivative at this point where u is pointing in that direction. So directional derivative at pi over 2, pi over 2, 1 is going to be the gradient at that point dotted with the direction. The direction is 2I minus 2j plus k divided by its magnitude, which is root 4 plus 4 plus 1. Now, we already evaluated the gradient. The gradient was 0, negative 3, negative 2. We'll have to take the dot product of that with 2, negative 2, 1. We will perform the operation, but we don't need to simplify. They did not ask us to simplify. So this would give us 0 plus 6 minus 2 all over 3. So 4/3. So that would be our answer. Okay, so the next part of the problem is asking you to find the minimum directional derivative at that point. So the minimum directional derivative is minus magnitude of the gradient at the given point. So all we got to do is to find the magnitude of the gradient and then negate that. So that would be minus root 0 plus 9 plus 4, I believe. So gradient was found as 0, negative 3, negative 2. And that is going to be minus root 13. So that's the answer to this part of the problem. Use the method of Lagrange multipliers to find the points on this curve that are closest to 0, 2. So we have the curve y equals x squared minus 1. We have this curve. And the intersection with the y-axis is 1 and negative 1. And we are trying to find the point closest to 0, 2. So it is this point, or maybe a little bit higher right here. What are we trying to maximize or minimize in this case? We are trying to find the shortest distance. We are trying to find the closest point. So the thing we are trying to maximize is the distance. So we'll have to find the formula for the distance. If this point is xy, the distance is x minus 2, x minus 0 squared plus y minus 2 squared, and then take the square root of this one. So we'll take the underneath the square root. So f of xy equals x squared plus y minus 2 squared. And we need to minimize this function subject to the constraint. What is the constraint? The constraint is y minus x squared plus 1 equals 0. So this is our f, this is our g, and they did ask us to use Lagrange multipliers. So what we do is partial of the f with respect to x, partial of f with respect to y, and these would have to be lambda, partial of g with respect to x, negative 2x, lambda, partial of g with respect to y, which is just 1, and then the constraint, y equals x squared minus 1. We'll go ahead and solve this system, and then that would give us our answers. So the first one gives us 2x times 1 plus lambda equals 0. So this means either x is 0 or lambda is -1. Now we take two cases. If x is 0, then y would be -1. So we'll have to find the distance from 0, -1 to the point that they gave us. And this would be 0 plus 9. So this is 9. It's -1 minus 2, which is -3, and then you square that, you get 9. So that is one possible answer. Now we'll have to look at the other case. If lambda is equal to -1, so what happens if lambda is equal to -1? We'll plug it into the second equation. We get 2y minus 4 equals -2, -1, and that gives us y equals 3 halves. If y is 3 halves, we get x squared equals 5 halves. So that gives us x equals plus or minus root 5 over 2. Now if we evaluate f of that, plus or minus root 5 over 2, and then 3 halves, we get x squared plus y minus 2 squared, x squared, so this squared, plus y minus 2 squared, 3 halves minus 2 squared. So that's 5 halves plus, so 3 halves minus 2, that's -1 half squared. That's 5 halves plus a quarter, which is 11 over 4. Now, which one is shorter? Well, the distance of the second one is shorter because 11 over 4 is less than 9. So because 11 over 4 is less than 9, so the points are the second points. The points are plus or minus root 5 over 2, 3 halves. Okay, next problem. Consider the solid D that lies inside this sphere x squared plus y squared plus z squared equals 2z. So the sphere is x squared plus y squared plus z minus 1 squared equals 1. And above the plane z equals 1. So the center of this sphere is at 0, 0, 1. And the plane is also at 1. So this is z-axis, y-axis, and the x-axis. I've done a triple integral that is equal to the volume of D. Turn this triple integral into an iterated triple integral in spherical coordinates. So this is our solid right here. If we want to turn that into spherical, we'll have to find the limits. So the limits are from the plane, this is z equals 1, to the sphere, which we can get by turning the sphere into spherical. And then we'll have to find the limits of phi and theta. So let's do that. So z equals 1 gives us rho cosine of phi equals 1. That gives us rho equals secant of phi. X squared plus y squared plus z squared equals 2z gives us rho squared equals 2 rho cosine of phi, which means rho equals 2 cosine of phi. So these are the limits for rho. Now for phi, we'll have to take z equals 1 and x squared plus y squared plus z squared equals 2z and find the intersection. So this gives us x squared plus y squared plus 1 equals 2. So this is going to be r equals 1. So we have this. We have rho sine phi is 1 and rho cosine phi, which is z, is also 1. So what does that tell us? That means tan of phi is 1, which means phi is pi over 4. So this is the limit for phi. So now we are ready to set up this surface into the integral. So this is the volume. Volume is triple integral of 1 dv. And then we'll have to turn this into spherical. So this is rho squared sine phi d rho d phi d theta. The limits of phi are from secant phi to 2 cosine phi, as we found earlier. limits of phi are from 0 to pi over 4, and limits of theta are from 0 to 2 pi, because the projection onto the xy plane is a full circle centered at the origin. Turn this triple integral into an iterated triple integral in cylindrical coordinates. Okay, so in order to turn this into cylindrical coordinates, we'll have to find the bottom and the top. The bottom is given as z equals 1. So this one is z equals 1. The top is x squared plus y squared plus z squared equals 2z. But we will have to solve this for z. So this is x squared plus y squared plus z minus 1 squared equals 1. And because it's cylindrical, we have to turn this into r theta z. So z minus 1 squared is going to be 1 minus, this is r squared, so this would be r squared. And because it's the top half, z is more than 1. So z would be 1 plus root 1 minus r squared. So this is the second limit for z. And then we need the limits of r and theta, which come from the intersection. So the intersection is, as we found earlier, the radius here is 1. So the intersection is a disk of radius 1. So this radius is 1. So the triple integral of xyz dv is going to be, so x is r cosine of theta, y is r sine of theta, z is z, r dz dr d theta. Limits of z are from bottom of 1 to the top of 1 plus root 1 minus r squared. Limits of r from 0 to 1, and limits of theta from 0 to 2 pi. Okay, so let's move on to the next problem. Find the surface area of the part of the cone that lies in the interior of the cylinder. So let's do that. So first we're going to draw the cylinder. So this is our cylinder. And we have a cone. So it looks like this. And we are trying to find this surface area. This is the surface area that we are trying to find. So what is the surface area, the formula for the surface area? It is surface integral of 1. And let's call this surface sigma. So surface area is surface integral of 1 ds. So we'll have to parameterize this surface. So sigma is given as r of xy equals x comma y comma, because this is z equals something, it would be this 2 times x squared plus y squared. So this is our parameterization. Next, we'll have to find the normal vector and then magnitude of that. So r comma r sub x cross r sub y, we have a formula for that, is negative fx. So that's root 2 1/2 x squared plus y squared to the power of negative 1/2 times the derivative of inside, negative fy 1/2 x squared plus y squared to the negative 1/2 times 2y 1. We'll have to take the magnitude of this. Rx cross ry is going to be square root of, the 2's cancel. Squaring that, we get 2x squared over x squared plus y squared plus 2y squared over x squared plus y squared plus 1. And this gives us root 3. So that's the magnitude of that. So surface area becomes double integral over the region, which is the projection onto the xy plane, and this is the region. So the intersection of these two is just this, is just x squared plus y squared equals 1. So the region on the xy plane is x squared plus y squared less than or equal to 1. And then ds, which is root 3 dA. So what is this? This is going to be root 3 times area of the disk of x squared plus y squared less than or equal to 1, which is pi. So root 3 pi is going to be the answer. Okay, so next problem. Use Green's theorem to evaluate this integral. And they said C is the circle of radius 2 oriented counterclockwise. So because it's oriented counterclockwise, the orientation is in fact positive. So what do? We apply, and this is in 2 dimension, we apply the Green's theorem as instructed. So it would be double integral over over this region that's called at R, over the circle, of partial of this one with respect to x, which is negative 3x squared, minus partial of this one with respect to y, which is negative 3y squared dA. So this would be 3y squared minus 3x squared dA. Now, in order to evaluate this one, we'll have to switch to polar. Radius is given as 2, so 0 to 2 pi, 0 to 2, 3 times, so this would be r squared cosine squared theta minus r squared sine squared theta r dr d theta. So by the half angle formulas that we have used in class, we can get that to 3r cubed times, this is cosine of 2 theta. So this is the double angle formula or the half angle formula. Each one of these are, this one is 1 plus cosine of 2 theta over 2. If you don't remember that cosine of 2 theta is equal to that, you could also get it this way. This is 1 minus cosine of 2 theta over 2. And once you subtract, you get cosine of 2 theta, dr d theta. Okay, so the first integral is very easy to evaluate. In fact, the second one is also not that difficult. So this is 3r to the 4th over 4 times cosine of 2 theta from r equals 0 to r equals 2 d theta. Once we evaluate this, we get 3 times 16 over 4, and this would be sine of 2 theta over 2. Because at 0, when r is 0, is just 0. And this is from theta equals 0 to theta equals 2 pi, which is clearly just 0. The second part of this problem is asking us to evaluate this integral, where c is a smooth curve from 1 to negative 1 to 0, 1, 2. So because they didn't give us the curve, it is clearly an instance of the fundamental theorem of calculus. So we will use the fundamental theorem of, line integrals. So f sub x would have to be 2xy. That would give us f equals x squared y plus g of y comma z. F sub y is x squared minus c squared. So plug that in here. We get x squared plus g sub y is equal to minus c squared, x squared minus c squared. So that means g is minus z squared y plus h of z. And we also know f sub z is equal to negative 2yz. So f becomes x squared y minus z squared y plus h of z. So taking the derivative with respect to z, we get minus 2zy plus h prime of z is equal to minus 2yz. So this gives us h prime of z equals 0. So a potential function is x squared y minus z squared y. So this is a potential function. Now, when you want to find the line integral, you'll have to plug in the endpoints and subtract. So the line integral of f dot dr is going to be f of the terminal point, which is 0, 1, 2, minus f of the initial point, which is 1, 2, negative 1. And then we plug it in there. We get 0 squared times 1, that's 0, minus z squared, which is 2 squared times 1, minus 1 squared times 2, minus negative 1 squared times 2. So this would be minus 4 minus 2 minus 2. So the answer is negative 4. Okay, last problem. Let C be the curve that is the intersection of the plane and the cylinder oriented counterclockwise when viewed from above. Use the Stokes theorem to turn this line integral into a surface integral, and then you do not need to evaluate the um, integral. You do need to turn it into an iterated double integral, but you do not need to evaluate it. Okay, so the first thing is to draw the diagram. As usual, you'll have to draw a diagram. It is very important to draw a diagram. It doesn't have to be perfect, but you have to include something to help you understand what's going on. So we have a cylinder here, and then we have a plane. Now, if you don't exactly know where the intersection with that plane is, it doesn't really matter. It's like a tilted plane. Now, is it going to be here? Is it going to be a little bit lower? Doesn't really matter. We need some visualization to be able to help us understand what's going on. And they said it is counterclockwise, so it would be this way. So if this is counterclockwise, the surface would be sigma and the orientation would be upward. So that's our sigma. Now we'll take the vector field and we find the curl of that vector field, and then we parametrize our surface, and then we write down the we use the Stokes theorem. So curl of f would be I j k partials y squared 2xy minus xz squared, which is what they gave us. And we will evaluate this. We get the first one gives us evaluate derivative with respect to y. We get 0 minus derivative with respect to z. We get also 0 I minus, eliminate the second column. We get minus z squared minus 0j. Eliminate the third column. We get 2y minus 2yk. So this is going to be z squared j. So this is our curl. Next, we are going to have to look at the, we have to look at the orientation and parameterize and orient and look at the orientation. So this is r of xy equals x comma y, and then we look at the parameterization. We look at the equation that they gave us. It is z equals 2 minus x plus y over 2. So this is the parameterization, and x and y are inside the circle, and the radius was 1. Now we'll have to find a normal vector. So rx cross ry, we have a formula for that. Negative fx, so that's 1/2, negative fy, and 1. Now we have to check the orientation. This is upward. So we can just take that and plug it into the formula. So curl of f dot n ds is going to be, okay, so this is over the disk, x squared plus y squared less than or equal to 1, and curl is z squared j, but because we are doing everything in terms of x and y, we'll have to replace z. So z would be 2 minus x plus y over 2 squared j dotted with the normal vector, which is 1/2, 1/2, 1, and dA. Now they said turn this into an iterated integral, so we'll have to turn this into polar. So 0 to 1, 0 to 2 pi, 2 minus r cosine of theta plus r sine of theta all over 2 squared multiplied by 1/2 r dr d theta. So that would be our final answer. I will see you in the next video.